Hello everyone and welcome to Chemical Reactions Part 2. In this packet we're going to learn how to balance equations. Remember we've seen the first part already. It's a two-part process. As I like to say, names to formulas, then balance. Okay, so you have the skills to complete the first step, which is names to formulas. So for example, here we have a carbon atom, which is just symbol C, oxygen molecule O2, and then carbon dioxide, CO2. I've got a nice kind of microscopic picture there. Okay. Now when we balance an equation, we're going to put numbers in front of these if necessary, okay, to make sure we obey what's called the law of conservation of mass. Now that's a very kind of simple concept. From the start of chemistry, chemists always noticed that the mass of the reactants, that's these things here on the left of the arrow, mass of the reactants always equaled the mass of the products. Now the question is, why is that? It's because atoms aren't created or destroyed. If I start with one carbon, I end with one carbon. If I start with two oxygens, I end with two oxygens. And the trick with chemistry is when we balance an equation, what is a reaction? It's just turning reactants into products. We just have them stick together differently. So it's the same number and type of atoms here, same number and type of atoms here, one carbon, two oxygen, two oxygen. But remember from the periodic table, that thing weighs 12, and it still weighs 12 when it's stuck in there. That weighs 16, as does that. It still weighs 16 here. So two atoms of oxygen and one atom of carbon actually weighs 44 if you add it up. That's the same as one atom of carbon and two atoms of oxygen here. All adds up to 44. Okay, so that's what we're going to concentrate on, making sure we've got the same number and type of atoms before and afterwards, because the same number and type obeys the conservation of mass law. It weighs the same. Okay, now just a quick reminder, a balanced chemical equation, which was our goal here, same number and type of atoms of both sides. We can break this down a little bit. Remember, a carbon just represents a single atom of carbon, CS. It's a carbon in a solid. Remember our brick example. This is actually the same example from the first week of class, if you remember our first ever balanced equation. A molecule of oxygen, there it is, okay, goes to one molecule of CO2, okay. So, as you mentioned, since there must be, by definition, the same mass of reactants and products, there is, by definition, the same mass of atoms, the same number and type of atoms, both sides. Now we can kind of look at that in a very simplistic way. Let's look at this question here. If you remember, hey, mass of reactants equals mass of products for any reaction. If I've got 5 grams of carbon, and I end up with 18.3 grams of CO2, what mass of O2 was formed? Real simple, think about it. Remember, you have the power of the pause button. You can do that, right? So pause it and then answer that question, okay? All right, real quick. Something plus 5 equals 18. All right, what could that be? So it's 13, isn't it? So that's going to be 13.3 grams. 13.3 plus 5 is 18.3 grams. Okay, so that's called the conservation of mass, okay? Conservation of mass. Okay. Now, as you move on, we get to that one, and I think in one of the classes, I can't remember which one. Okay, we have 2 groups of Chem 100, remember? Okay. We got about here last time, the others didn't quite get here, but this is a super important concept because it really kind of shows you have to learn to walk before you learn how to run. And that balancing an equation is truly a 2-step process, okay? Names to formulas, then balance, okay? So the rules for making a balanced chemical equation. First, and it's what we learned already, we've done this in the last packet, construct an unbalanced equation, i.e. just turn names to formulas. Okay, now that's the first step. If you're a big fan of the original Star Trek, you can change the laws of physics or chemistry, right? Once you've got that formula down and it's correct, don't be tempted to change it. Okay, so let's try that. Let's just try that very simple names to formulas here. Okay, write the formulas of these three things. If you need to pause for a second to do that, do that. Okay, and then we can check with what I get. Okay, so magnesium, check the periodic table. Mg. Oxygen gas, so on the previous page, O2 gas. Now, some of you may have been tempted to do two things at once. Oh, magnesium plus O2 makes MgO2, right? No, it doesn't, because you've got magnesium oxide. You know, magnesium's a +2, right? Oxide is a -2. It's a 1-to-1 ratio. So that's the formula of magnesium oxide, okay? +2, -2. I know your brain is saying it's not right, and your brain's correct. It isn't right because it's not balanced. You've got 2 oxygens here and only 1 there. Okay, but this is your unbalanced equation. Okay, we've done correctly names to formulas. Okay, and that's what we've been doing so far, and that's what we did at the end of the last packet. Turns out that all the examples at the end of the last packet, if you want to check back, were already balanced. Okay, they already had the same number and type of atoms before and afterwards. This is the first one that doesn't. Okay, all right, so remember the trick. Always convert, and I'll show you the last bit down here. You know how to identify and write the name of either ionic or a covalent material, or even an element, in this case also magnesium. Okay, just turn names to formulas first. That's the first step. Yes, I know it's not balanced. That's step 2. Okay, so step 1, names to formulas. All right. Now, we do the actual balancing. And this is the first time we've done this. Okay. What I like to think about is what I call the tennis approach. Okay. So we're going to get the same number and type of atoms on the left and on the right, before and afterwards. Okay, and a nice way to do this actually is to draw a little picture. All right, so I've got Mg plus O2 goes to MgO. That's what I got from my first step. Okay, what's Mg? It's just an atom of Mg, right? What's oxygen? It's just 2 oxygens stuck together. And MgO is just an Mg and an O stuck together. Okay, now tennis, what do I mean by that? Think of like a tennis net here. We're going to go backwards and forwards over the net, change thing over here, see how it affects things over here. Just pick what's easiest. Magnesium. How many magnesiums are here? And later on you'll just kind of put the number. We've got 1 magnesium and we've got 1 magnesium there. Sure, it's hooked up differently, but hey, number and type of atoms, 1 magnesium. We say right now this is balanced with respect to, just thinking about it if you like, magnesium. Now look at oxygens. How many oxygens here? 2. It's written O2, right? Because there's 2 oxygens. We write 2 oxygens if you like. Okay. Interesting. Look over here. We have 1 magnesium oxide. Think of this as a car with 1 oxygen passenger. So there's only 1 oxygen. Oh no, we can't change the formula. We can't put a 2 here, remember, we can't, right? That's got to be a 1. But think about it. How many cars with 1 oxygen passenger do I need to have 2 oxygens? Remember, same number of oxygens before and afterwards. The answer is 2, right? So I need another MgO. Vehicle 1, 1 passenger. Vehicle 2, 2 passengers. What does that mean? 2. Ah, that's what that means. So the number in front means 2 vehicles, 2 of everything. Okay? 1 magnesium oxide unit, another magnesium oxide unit. Fair enough. So now we've got 2 oxygens, 1, 2, balanced with respect to oxygen. Fantastic. But what did we mess up? Back over the net again, right? We've got 1, 2 magnesiums. How many over here? Oh, interesting. Magnesiums fly alone, right? They're just by themselves. So how many things by themselves do we need to get 2 things? 2. Another Mg. All right, there we go. So that's our answer. 2 magnesiums, if we like, we can just reinforce. 1 O2. Okay, so that's 1 vehicle with 2 oxygen passengers. 2 single magnesiums. 2 magnesium oxide units. There we go. So that's your first proper balanced equation. So we can put that back over here. 2, 1, 2. And this is a skill we use in chemistry all the time, okay? So be very familiar with this by finals time, or actually last midterm time, no final, right? But there you go. So apply what I call the tennis approach, balance a single type of atom on the left, and see what you need to do on the right. Make it happen on the right. Do you have to come back again, just like we did? Yes, you do. So we balance magnesiums, we balance oxygens, and then we balance magnesiums again. We went backwards and forwards a couple of times. Okay. And there's a nice little picture, better than the one I did on the rough paper. 2 Mgs, 2 Mgs, 2 Os, 2 Os. Hey, same number and type of atoms. 2 singles, 2 Mg. 2 in the vehicle, so 1 vehicle with 2 passengers. The subscript is the passengers, if you think about it. It's 2 passengers, 1 vehicle. Put 1 there. And then 2 MgO vehicles, 1 Mg and 1 O per vehicle. Okay, that makes sense. If you were lucky enough to see this in lab, magnesium, in fact, if you remember, is actually used in flares and such. Okay, it burns with a very bright flame. So when you took that magnesium metal from lab, okay, and you burnt it in lab, or watch me burn it in lab, okay, the magnesium reacted with oxygen molecules from the air, and that's where the reaction is happening. These things are bumping into each other and sticking, and what do they make? That kind of white powder you ended up with. We called it a smoke in the lab there, but hey, that powder, a fine powder, is actually a smoke. Okay, so there's magnesium and oxide ions. 1, 2, 1, 2. I think it's a giant ionic material. So there it is. Pull that up so you can see it. There it is. Okay. Now, if you feel confident with this, feel free to give it a shot. I'm going to go through them now, but now for you is whenever you like. Just press pause and try it, and then just run it and see how I did it. Okay. So the first one, the combustion of hydrogen to make water. This is actually how the space shuttle works. Okay. In the space shuttle tank here, we have hydrogen, liquid hydrogen, and liquid oxygen. Okay, they're both in that tank there, and it's kind of split in a kind of a 2-to-1 ratio. Okay. Now, of course, when the shuttle goes into space, there's no air out there, so it can't use a regular jet engine, so it takes this air with it, if you like, or just the good part from the air, the oxygen it needs to burn hydrogen. Okay, so the combustion of hydrogen. So we're going to burn hydrogen. Combustion means add oxygen. So hydrogen gas, it says gas, hydrogen gas. Combustion means add oxygen. So we're doing that unbalanced equation to make water. Now be very, very careful here. You know the formula of water, right? It's H2O. At that temperature, probably a gas, steam. Okay, if you were tempted to kind of skip and try and do 2 things at once, you might have written H2O2, which is hydrogen peroxide, right? Obviously, there's no hydrogen peroxide flying out the back of the space shuttle because everything for a 50-mile radius would be dead, okay? So names the formulas. Water is H2O2. Remember that whole balancing thing makes it right in terms of the number of atoms of each type, but we've got to put numbers in front. So let's do the tennis thing. Nice little trick, always do oxygen last. So look on the left, how many hydrogens, and you can draw a little picture if you want. Hydrogen, 2 H's stuck together. Over here we've got H2O, you may remember as something like that. Well, water has 2 hydrogens in it already, and 1 oxygen. 2 hydrogens over here. So for hydrogen right now we're okay. We say it's balanced with respect to hydrogen. Look at oxygen. Unfortunately it's not balanced with respect to oxygen. 2 oxygens here, only 1 here. So it's the same as the last one, isn't it? If you remember, hey, we've got 1 vehicle with 1 oxygen passenger. We need 2 oxygens. Yeah, we need 2 vehicles. Okay, 2 water molecules. Let's put 2 in front. Now I have 1, 2 oxygens. Good to go. 2 oxygens. Good to go. Alright, but what did I mess up? Hey, careful here. 2 vehicles. Each vehicle contains 2 hydrogens, so that's 4 hydrogens. I've only got 2 over here right now. Hey, 2 per vehicle. I need another vehicle. I need 2 hydrogens. There we go. So 2H2, put 1 there if you like, 1O2, 2H2O. Okay, so in the back of the packet, if you want to kind of do it a little bit neater, okay, I got a thing for balancing water. So you got 2H2 plus 1O2 gas goes to 2H2O gas. So 1, 2, nice to draw a picture, right? 1, and then H2O, and another one. So there's a picture of balancing water. Okay, now important, right? When we look at this, for example, when we look at 2H2O, remember this is in the appendix in the back of the packet, so dig it out if you need to. Okay, what does that mean? Well, H2O is the formula of the molecule, right? So an H, an O, and an H, all right? So one H2O, put one there, it's just one molecule. 2H2O means 2 molecules, and that's exactly what we have up here, okay? However, H2O2, that means 2 hydrogens, 2 oxygens in the vehicle. That's what hydrogen peroxide would look like, right? Which is not what we've got here. So remember, subscript is the number of passengers in the vehicle, with the formula, if you like, being 1 vehicle. If I got a 2 in front, it means 2 vehicles. 1, 2. Okay, so that explains subscripts, the number of passengers, and prefixes or coefficients, the number of vehicles in our analogy. All right, so if we look at balancing water in a little bit more detail again, two H2, 1 O2, so let's write the equation. Two hydrogen molecules, 1 oxygen molecule, 2 H2O. It's balanced. It's obeying the conservation of mass. I've got 2 oxygens, 2 oxygens. 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens. It weighs the same. Okay, it weighs the same. Same number and type of atoms weigh the same, hence conservation of mass. So when you hear conservation of mass, it's really saying same number and type of atoms before and afterwards. If you remember same number and type of atoms, you're always going to be right. Okay. All right. Let's continue. Okay. So we have a couple of pages of work here. Okay. If you're feeling confident, try it. Okay. If you need one more practice, maybe watch this next one and then pause it and have a go. Okay. Combustion again of sodium metal. So it's sodium, solid, just from the periodic table. Combustion, O2 gas, turns into now oxide, right? It's oxide. So when you burn something, you add oxygen to it. So sodium's going to make a +1 ion, oxygen's going to make a -2. Do the math down here quick, right? How many +1s cancel -2? Oh, 2 of them. Okay, 2 of them. So that's the formula of sodium oxide. Okay, nice trick. Always leave oxygen till last. One, if you like, you know, put a 1 in front. 1 sodium. Oh, 2 sodiums. One formula, if you like, has 2 sodiums. So I have to change that. 2 sodiums, right? 2 by themselves, 2 inside the 1 vehicle. So sodium, 2Na, 2Na, good to go. It's balanced with respect to sodium. 1 oxygen molecule, so that's 2O. Oh look, there's only 1 in there, so I'm going to need 2 molecules, or 2 formulas if you like, to get 2 oxygens. Mixing 2 oxygens. Fair enough. So now I've got 2 oxygens, 2 vehicles with 1 per vehicle, and then 1 vehicle with 2 again. But now what have I done real quick? I've just messed up the number of sodiums. I've got 2 vehicles, 2 sodiums per vehicle, that's 4 sodiums. So I need 4 over here. I have to change that to a 4. So your prefixes, your coefficients of 4, 1, 2, 4 sodiums. 2 times 2 is 4 sodiums. 1 times 2 is 2, 2 times 1 is 2. It's balanced. So it's 4, 1, 2. All right. Now, oftentimes, and we tend to like these questions because they're quick to write and quite important in terms of organic chemistry. So organic chemistry is the study of natural materials. Natural materials, or organic materials, contain carbon, hydrogen, and sometimes oxygen. Okay, now if you think about it, everything you eat is organic, all right? So you eat some sugar, which is a carbohydrate, which contains carbon, hydrogen, and oxygen, all right? And then when you metabolize that, you're basically internally burning it, okay? And what do you give out? Carbon dioxide and water. What comes out of your breath in your breath is carbon dioxide. That's what happens when you burn carbon, you get carbon dioxide, and then water, which happens when you burn hydrogen, okay? If I have fuel like methane, which comes out of your stove, that's called a hydrocarbon. Okay, so a hydrocarbon, maybe I'll write it down here just out of the way a little bit. Okay, so we've got some amount of C's, X, and some amount of hydrogens, Y. That's called a hydrocarbon. I'm always going to get carbon dioxide and water as products, because when I add oxygen to carbon, CO2, when I add oxygen to hydrogen, H2O. A carbohydrate just has a little bit of extra oxygen in it, which helps combustion actually. They burn a little easier. Carbohydrate. Obviously the numbers will change for each example, but basically if it's just carbon and hydrogen, hydrocarbon, CHNO, carbohydrate. Same idea though. You always burn these things if you like they're fuel for machines. Think about your stove, think about your car, which uses octane, which is 8 carbons. Or carbohydrates, sugar, alcohol, things like that. Okay, so I'm going to hide the answer there. All right, okay. So, actually, let me get it. So, we can leave it there. Okay, let's do it. So, the combustion of methane. So, methane is given, CH4. That's a gas, that's what comes out of your stove. If you ever light your stove, this is what's happening in that blue flame. Combustion. O2 gas. Now the products of combustion for any carbohydrate or hydrocarbon, as in this case, are CO2 and H2O, that temperature gas, right? Okay. Now here's the big trick. Big trick. Always balance in the same order carbon, hydrogen, oxygen. It's kind of the same order as found in the formula. Okay. If you do it carbon, hydrogen, oxygen, a lot of the tricky stuff will take care of itself, and let's show you how that works. So for carbon, I got one, I'll just do it down here, one, because I got a picture in a second, right? We'll show you the picture in a second. Got one carbon over here, I got one carbon over here. So far, so good, right? Hydrogen's next. For hydrogen, I need 4 hydrogen. The only place hydrogen appears is in water, and there's 2 hydrogens per vehicle, right? So I need 2 vehicles. 2 hydrogens inside, 2 molecules, 4 hydrogens altogether. Okay. Interesting. So now what we've got to do is balance the number of oxygens. We've got the right number of carbons, 1 each side. We've got the right number of hydrogens, 4 each side. Now think about it. What have we done over here? Because we have to have 1 CO2 and 2 waters to balance the number of carbons and hydrogens, we've locked in some oxygen. How many oxygens we locked in? 2 there, and then 1 per molecule, 2 molecules, 2 there. So I've got 4 oxygens. Oh, why do oxygens last? Because of this locking in thing, right? So I need 4 oxygens over here. Interesting, oxygens travel in pairs. So how many vehicles with 2 passengers, how many molecules with 2 atoms? It's 2. 1, 2, 1, 2. And let's show you a nice picture. 1, 2, 1, 2. Let's check it. 1 carbon, 1 carbon. 1, 2, 3, 4 oxygens. 1, 2, 3, 4 oxygens. 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens. Good to go. All right, so that's your first example of an organic. Don't forget with organics, it's always carbon balance first, hydrogen second, oxygen third. Oftentimes, when you've locked in that amount of oxygen here, it makes that last step easier. So oxygen's all over the place. If you do it first, it's tricky. If you do it last, it's easy, okay? All right. So a couple of little harder examples. The combustion of sugar, it's a hydrocarbon, okay? So C6H12O6 solid plus oxygen gas turns into, again, combustion of an organic, always carbon dioxide and water, okay? Carbons first. How many carbons? 6 carbons. So I need 6 carbons over here. 1 molecule so far with 1 carbon. Oh, I need 6 molecules. Okay, carbon's good. 12 hydrogens. Okay, I need 12 hydrogens. 2 per molecule. Oh, I need 6 molecules then. Good to go. Now remember, we've locked in 2 times 6 is 12 oxygens, and another 6 is 18 oxygens, right? So we need 18 oxygens over here. Now here's another trick I like to use, okay? Before we just said, oh, you know, here's the oxygen, but wait, there's 6 already in here, so we have to think about 18. I don't think about 18 as 18, I think about it as 6, which is what I need here, plus what I need to get to 18, which is 12, okay? So if I take away the 6 I need here, that leaves me with 12. Oh, then it's, hey, 2 times what is 12? It's 6. So the balancing numbers are 1, 6, 6, 6. Interesting. Interesting. Okay. Next one. Now, don't be confused by this. Aluminum, of course, is a metal, right? It's not organic, so only things with carbon and hydrogen make carbon dioxide and water. If I burn aluminum, whenever I burn something, add oxygen, I make its oxide. So aluminum and oxygen, think about it. Hey, it's an ionic compound. -2 plus 3. Oh, it's that 2,3 thing. There we go. Okay. So those are the formulas. Combustion, add oxygen. Aluminum, right? Aluminum oxide. It's ionic material. Remember, anything with a metal is going to be ionic, right? Okay. So I need aluminum first. Oh, 2 aluminums. There we go. You can almost just do this just looking at it now. Now we have a problem. 3 here and 2 here. So it doesn't work with whole numbers. So remember what we did when we actually made this formula? We did lowest common multiple, right? So the lowest common multiple of 2 and 3 is actually 6. So I want 6 oxygens here and 6 oxygens here. Well, that's easy. 6 oxygens is 3 times 2. 6 oxygens, well there's 3 inside the vehicle, so I need 2 vehicles. Fantastic, that's 6 and 6. Obviously, just messed up my aluminum. 2 inside, 2 vehicles. I can do that, 4 aluminum. So the answer is 4, 3, 2. All right. Next one. That annoys me, it's reacting. If I react sodium metal with water to give sodium hydroxide and hydrogen gas, how does that work? Now this one, it's one examiners love to test, okay? But it's kind of tricky to balance it because it's a single replacement. Okay, so single replacement reaction is a little tricky, okay, but let's show you how to do it. Okay, so sodium metal plus sodium hydroxide. Oh, sorry, sodium metal plus water, my mistake, H2O, turns into sodium hydroxide. Hopefully you remember this one from before, +1 -1. Hydroxide, OH, plus hydrogen gas. Tricky. Okay. Now, a nice way to think about this, if you remember when we did our acid plus base, salt plus water, okay, you can think of water as being made of H stuck to OH, right? So what I'm going to do, I'm going to balance the OHs, I'm going to balance the H's by themselves. Let's do that. Okay, so 1 sodium, 1 sodium, 1 sodium, 1 sodium, good to go. All right. Here, 1 OH, 1 OH, good to go. Here, 1 H, 2 H's. Oh, that's the problem, right? Because I got 1 hydrogen with 2 H's. There's my hydrogen, right? So I'm going to need 2 of these things. So I get 2 H's, 2 H's. That gives me 2 hydroxides as well. So 1 in there, so there's 2 there. Put the 2 there. So 2 sodiums, 2 sodiums. Now, my recommendation is you actually kind of try and memorize this one.